In this video, I'm going to introduce us to the idea of having an algebra of our group. And so if we have two independent groups, A and B, where A has its order is A in the bars like that, and B has this order here, we can form a set of A and B when they're combined together like this. And if the two groups are commutative, so in other words, it doesn't matter which order you combine them, then the set of I times J products will form a new group, which is called the direct product of A and B, and we denote it with this A cross B. So the group properties are satisfied. So if we take A combined with B here, and then this separate A combined with a different B here, and they're in parentheses, and we just set those equal to each other. So we're doing the combination of all four of them here. Because we postulated that these need to be commutative, we can move this B and this A around so that we end up with this. And then we have this A sub P, B sub Q here, where both of those are elements of their respective groups. Then I show here that we can do that with the identity element. So we get the identity elements here. We can move the identity elements around because we said it was commutative. And so we just get our A sub I and B sub L back again. And we can do that also with our inverses here. So we have A sub I and B sub J, and then in this parentheses the A sub I inverse and B sub J inverse. And so once again we can move those around because we said they were commutative, and we get the combination of both identity elements here. And so to make it a little more concrete, if we take our C3V group that we've been using as an example, we can add another symmetry, which is this sigma sub h, in a group that I'll call uppercase sigma sub h. And this new symmetry reflects the triangle across a plane parallel to the page. And so essentially we go from our triangle here, and we sort of the part sort of facing us out of the screen now is facing into the screen, and the part facing into the screen is now facing out of the screen. And so I represented that here with it kind of grayed out. I sort of changed that little plus sign there into a little circle there. And so that is the symmetry operation that we're doing. And so we can take that and our C3V, and we can do essentially what I was showing sort of more generally up there. And so we can see that if we do this operation twice, we just get back the identity element, because if you just reflect this and then reflect it back again, you just get back to where you were. We can see that it commutes with C3V, since if we rotate by 120 degrees to counterclockwise, and then we do this operation, it would be the same as if we did that operation first and then rotated 120 degrees counterclockwise. And so those two things commute, and you could show that that is the same for every element of our C3V group. And so we'll just kind of, take it on, I don't want to say faith. I think it'd be easy to show, but I'm not going to go through that just for the sake of time. So we have our two groups here, and we have a group that is the C3V cross with our uppercase sigma sub h, and it will have the order of C3V times the order of our uppercase sigma sub h equal 12 elements. And so it'll have here first all just the elements of our C3V group, and then we have just the sigma sub h here, and then the sigma sub h combined with all of the other elements of our group here, since if you combine those, it will give you something different than if you just do one of them or the other one of them. And so they can be sort of combined into a separate symmetry operation. So we now have this 12 element group here. All right, so kind of switching gears a little bit, so the real numbers, which is represented by this R here, form a group under addition, and the real numbers without zero form a group under multiplication. If we add 0, then it becomes a field, which I use this sort of fancy F here, where both addition and multiplication are defined and are associative and distributive. And so with both addition and multiplication, they're associative, and with addition and multiplication, it is distributive. And in fact, this field of the real numbers is a commutative field, so it doesn't matter which way you add or multiply them. And the same would be true if we used complex numbers. But so the reason I went through that is so we can define laws of combination between our group elements and the field of complex numbers. So this is a field of complex numbers here. And so we can take x equals some complex number times the first element of our group plus some complex number times the second element of our group, and sort of do a linear combination with every element of our group. We could do that here with this combination, or we could take a different combination of complex numbers. It could be something that's almost exactly the same, but just one of them are changed or something like that. But the idea is we could have all different numbers on here times each element of our group. So the group algebra associated with G is defined by specifying how the elements are combined. And so that would mean things like if it's distributive and associative, and whether that's under addition and under multiplication and things like that. So with these properties, we can define the sum of x and y up here. And so that's just taking the first one here, the first group element, and just adding the coefficients in front of them, then adding the coefficients in front of the second one here, multiplied times our second group element, and so on all the way up to our last group element here. Where this z equals x plus y is another element of the algebra with coefficients of z equals whatever the x plus y is for the coefficient of that group element. And so the product law then is essentially just doing FOIL, which we can represent more compactly like this. And we can see, for example, if we want to make it more concrete using our C3V group here, if we have x equals the identity element plus 2 times our rotation, and then y equals the identity element plus 3 times this first reflection here, then the sum is we just add the two identity elements here, so we end up with 2. We still have just a 2C3 because we can't sort of add that to any of the other things on here. And then the 3 sigma 1 here is still there. But the product rule, so we just put these together and we sort of FOIL it out. So everything else is just kind of getting multiplied by the identity element, and so it just stays the same. But then this last term here, when we take this 2C3 times these 3 sigma 1, so we end up with these two here. We can just multiply the coefficients, and then we can just sort of act the C3 on the sigma 1, which gives us sigma 3, and so we end up with this right here. And so these group elements in these up here, in these sort of algebraic rules up here, are called the basal units of the group algebra. And as you may have noticed, these are very analogous to the basis vectors in linear algebra. And I'll actually be sort of talking about how group theory and linear algebra sort of come together very nicely, even more in actually in very soon in this video series. But this is already sort of hinting at how that actually happens, where you can use these group elements as sort of like basis vectors here. And so just like in linear algebra, the basal units can be freely chosen from any group of the same order, and so our C3V group here, which is order 6, so we could interchange the basal units for another group G that's order 6, as long as each group element is linearly independent. And I'll talk a bit more about sort of linearly independent here in a future video coming up soon. But anyway, this is, like I said, just a brief introduction to sort of the algebra of a group. We'll be looking more deeply into this in future videos in this series, but it's essentially just defining how we combine the different elements of the group, and we can, turn it into an algebra by adding this field as sort of a second bin from which we can pull elements, which in this case could be something like the real numbers or the complex numbers. And so, if you want to keep it real general, you always use the complex numbers, because the real numbers are just the complex numbers where I is always multiplied by 0. But anyway, I don't want to harp on that too long. So I hope you found this video helpful, and I will see you in the next one.